Imagine a slow-motion tidal wave, quietly building for decades, and now it's just sweeping across the globe. We're talking about billions, literally billions of people affected by obesity, millions more grappling with diabetes. It's a health crisis on a scale we've never really seen before. Now, here's the real kicker. What if we told you that the seeds of these adult diseases, the very roots of this global challenge, are often sown long before birth, like even before a child takes their first breath? Today, we're embarking on a really crucial deep dive into two interconnected, incredibly powerful concepts: metabolic syndrome and the developmental origins of health and disease, which, well, we'll just call DOHaD to make it easier. Our mission is to unpack how those earliest life experiences can fundamentally shape our long-term health. We want to offer you, our future medical professionals, a new lens, a different way to view these complex conditions. And we're going to use some vivid metaphors, maybe some handy acronyms, and definitely some thought-provoking questions to make sure this knowledge doesn't just, go in one ear and out the other. We want it to stick. So to kick us off, here's a question to keep in the back of your mind as we talk. If we know that diet and exercise are absolutely key to managing obesity and diabetes, why does it so often feel like we're constantly fighting an uphill battle, often with, frankly, frustratingly limited success?
That's a great question to start with. And what's truly fascinating here is that this isn't just about the genes you inherit. It's much more about the profound way the environment interacts with those genes. It creates kind of blueprint for health or disease that develops incredibly early in life. This deep dive will definitely reveal some truly surprising connections between what happens in the womb, those vital first 1,000 days, and the chronic conditions we see unfolding decades later in adulthood.
Okay, let's break down the energy equation first. It's pretty fundamental to all of this. Think of your body's energy budget. It's a lot like your bank account, right? A constant balancing act. So when your energy intake, the calories you eat, precisely equals your energy expenditure, the calories you burn through just living, breathing, moving, keeping warm, then your body weight stays stable. Simple. You're balancing the books. But if your energy intake consistently goes over your energy expenditure, well, your energy stores, mainly fat, are going to increase. You're accumulating a surplus, or in medical terms, adiposity. You're storing energy for later. And conversely, if your expenditure is consistently higher than your intake, those energy stores get used up. You start dipping into your savings, so to speak. Simple enough on paper, right?
It sounds simple, yes, but this balancing act isn't merely about conscious choices or willpower, not at all. It's governed by an incredibly sophisticated internal regulatory system. You can think of it as your body's built-in homeostasis autoguard. Let's call it the HE system, constantly working behind the scenes. This HE system involves some key players. The hypothalamus, that's the brain's control center for appetite. Then there's adipose tissue, your fat cells, which aren't just passive storage. They produce crucial hormones like leptin. And the gut, the GI tract, which produces a whole symphony of hormones, things like ghrelin, our main hunger signal, but also others like CCK, GLP-1, PYY336, oxyntomodulin. Each plays a really nuanced role in telling your brain when you're full or when you need energy. And this whole intricate dance is further influenced by signals from the brainstem, our senses, even cognition, learning, and other vital hormones like insulin, thyroid hormones, cortisol. It's complex.
Wow, okay. That is a complex system.
Okay.
So if it's designed so well to maintain balance, why does it seem to, fail so spectacularly in common obesity? Is there like a key player that often breaks down?
Absolutely. And that brings us directly to leptin. It was famously discovered back in 1994. You might remember the OBOB mouse story from your studies. A loss-of-function mutation in the gene for leptin led to severe early-onset obesity in these mice. What was truly remarkable, though, was that when they were given leptin injections, they responded dramatically. They shed significant weight.
And incredibly, although it's exceedingly rare, similar mutations, these loss-of-function leptin gene mutations, have also been found in humans, and they also show these amazing positive responses to leptin injections. So it sounds almost like a magic bullet. But hang on, if leptin is the I'm full signal, the satiety signal, why isn't just giving more of it the simple answer for the vast majority of people struggling with obesity?
That's precisely the paradox, isn't it? And it directly answers your earlier question about that uphill battle. For the vast, vast majority of people with common obesity, those without these specific rare genetic mutations, giving them leptin injections has little to no effect. This highlights a really crucial concept: leptin resistance. It's like having a broken receiver on your radio. The signal, leptin, is being sent out, loud and clear maybe, but the body, particularly the brain, isn't getting the message. It's not hearing stop eating or burn more energy. The body isn't simply ignoring the signal. It's just not perceiving it correctly. And that makes weight management incredibly, incredibly difficult.
Right. It's just astonishing that a hormone with such a profound role can have such a complex and often frustratingly resistant interaction in most people. Though on a more promising note, looking at treatments, we now have drugs like semaglutide. This medication mimics GLP-1, glucagon-like peptide-1, that's a hormone our stomachs naturally produce when we eat, signaling fullness. So semaglutide basically amplifies this signal, helping to increase satiety and also regulate blood sugar.
Indeed, and the scale of the problem really warrants these kinds of interventions. The numbers. They reflect the sheer scale of the challenge. We are undeniably in a global pandemic of these conditions. The statistics are truly sobering. We're talking over 2.5 billion adults globally are overweight or obese. That's, what, 43%? And 890 million obese, 16%. Here in the UK alone, 1 in 15 people have diabetes. And get this, 80% of the NHS's 10 billion annual diabetes budget goes to treating complications, not prevention, but complications. Simon Stevens' comparison, obesity is the new smoking. It couldn't be more accurate for this slow motion crisis we're facing.
And it's so important to stress, this isn't just about individual willpower or choices, is it? We live in what researchers call an obesogenic environment. I like to think of it as a sort of sneaky chef, subtly influencing our energy budget without us even realizing it. This environment has layers, right? There's the physical environment. Maybe limited access to fresh food, but an abundance of cheap, calorie-dense, processed stuff. Urban design that makes walking or cycling difficult. Then the economic environment. Healthy food often costs more, or is perceived to. Less disposable income for gyms or active leisure. And even the social environment. Things like social isolation can actually reduce physical activity and maybe lead to less healthy food choices.
And all these environmental pressures, combined with individual susceptibility, often converge into a very specific pattern of health challenges. That's exactly where metabolic syndrome comes into the picture. When we talk about a syndrome, remember, it's not just a random collection of symptoms. It's a specific, recognizable pattern, almost like a red flag. It indicates a cluster of dangerous risk factors, particularly for developing heart disease and type 2 diabetes down the line.
Okay, so to help you remember the key components for actually diagnosing metabolic syndrome, we can use the acronym HIM-AD. Think of these as the factors that collectively spell trouble. The H stands for hypertension, high blood pressure, generally over 420/90 millimillar Hg, although the IDF, the International Diabetes Federation, uses a slightly lower threshold, their 085. The I is for insulin resistance. This is often inferred maybe from high fasting insulin levels, or it can be measured directly with something called a hyperinsulinemic glycemic clamp test. That's really the gold standard for research, but you won't see it much in day-to-day clinics. Then M represents key metabolic markers. We're looking for elevated fasting plasma glucose, typically over 7.0 millimolar, and dyslipidemia. Specifically, high triglycerides over 1.7 millimolar, and low HDL cholesterol, the good cholesterol, right in the AD. That refers to abdominal obesity, often defined by BMI over 30, but importantly also by a high waist-to ratio. And D is for diabetes itself, either established type 2 diabetes or diagnosed glucose intolerance.
And a really crucial point about that A for abdominal obesity. It's the central adiposity, the fat accumulated around the abdomen, around the organs, that's considered more critical than just BMI alone. BMI is useful, sure, but it doesn't tell you where the fat is or distinguish it from muscle mass. Central fat, that visceral fat, is much more directly linked to insulin resistance, fatty liver disease, inflammation. It makes it a much stronger predictor of these metabolic problems. So it's not just about overall weight. It's where that fat is located that really rings the alarm bells. And this syndrome, metabolic syndrome, it's incredibly common. We're seeing it in maybe 20-25% of adults globally. And alarmingly, it rises to over 40% in adults aged 40 and above. And it's definitely on the rise. Its impact is dramatic. Having metabolic syndrome means you have a 5 times higher risk of developing type 2 diabetes. 5 times. And a 3 times higher risk of heart disease. It truly is this powerful synergy of sickness where these conditions don't just add up their risks, they seem to multiply the threat when they cluster together.
Wow. Okay, so given that complexity, it clearly demands more than just individual action. You need societal solutions too, right? What are some of the most impactful changes we could make at that population level?
Precisely. You can't tackle something this complex with just individual advice. Addressing metabolic syndrome requires a system-wide approach. That means things like promoting healthy diets at a population level, making healthier food more accessible and affordable. It means redesigning our environments, our cities and towns to actively encourage physical activity, making it easier to walk, cycle, play. And it also involves fostering cultural shifts, changing societal norms and values around food, around activity, around health itself. It's really about creating an environment where the healthy choice becomes the easy choice, the default choice, not the exception.
Okay, now let's pivot slightly and explore something truly, well, revolutionary in understanding all this. The developmental origins of health and disease, or DOHaD. This theory fundamentally shifts our understanding of chronic illness because it looks at its very earliest roots, literally, before we were even born. It really is a paradigm shift in how we think about disease etiology.
It absolutely is. The genesis of DOHaD really traces back to the early 1990s with the work of researchers like Nicholas Hales and David Barker. They made this striking observation. Low birth weight was actually a stronger predictor of adult metabolic diseases, things like cardiovascular disease, hypertension, type 2 diabetes, than even smoking was, which was incredible at the time. This profound finding led them to propose the thrifty phenotype hypothesis. The core idea is that a fetus, when it perceives limited nutrients coming from the mother via the placenta, it sort of programs its metabolism to conserve energy. It's essentially preparing for a life of scarcity, a life where calories might be hard to come by. It's fundamentally a survival mechanism.
That's just extraordinary. So how could something as seemingly simple as a person's weight at birth have such a profound, such a lasting impact on their health decades down the line? What are the mechanisms? How could fetal development possibly be linked so strongly to the chronic diseases we see so much of in adulthood?
This is where the concept of fetal programming comes in. You can think of the fetus almost like a chameleon. It's adapting its biochemical processes, the development and structure of its organs like the pancreas, the liver, muscle tissue, based on the nutrient supply it receives through the placenta. These adaptations, these adjustments made in response to the perceived future environment, are then effectively programmed into the individual. They set the individual's metabolic trajectory for life.
Okay. And this is the powerful answer, or at least part of the answer, to our earlier question about that uphill battle with obesity and diabetes. If that child who's programmed in the womb for scarcity then happens to grow up in our modern obesogenic environment with abundant, easily accessible, calorie-dense food, those thrifty metabolic adaptations, the ones originally designed for survival in a harsh environment, they can ironically backfire. They can lead directly to obesity, diabetes, metabolic syndrome. The body is still, in a way, expecting famine, even if it's never coming. And this mismatch could potentially exacerbate things like that leptin resistance we talked about.
Precisely. And tragically, we have compelling evidence for this from what are essentially natural experiments. The Dutch famine, the hunger winter of 1944-1945, is a key example. Studies showed that children born to women who were exposed to famine, particularly during early pregnancy, had a significantly increased susceptibility to diabetes, obesity, and cardiovascular disease when they reached adult life. The data clearly showed that exposure in early gestation was linked to higher adult CVD rates and higher adult BMI compared to those exposed later or not at all.
And while birth weight is a really useful indicator, a proxy measure, it's important for us to remember it's determined by many factors, not just maternal nutrition during pregnancy. There are other environmental inputs: overall maternal caloric intake before and during, exposure to alcohol, tobacco, drugs, even fetal hypoxia. Then there are genetic factors, like the mother's own pre-pregnancy weight, her birth weight, weight gain between pregnancies, plus maternal health conditions, things like intrauterine infections, anemia, gestational diabetes, and even placental factors themselves, like impaired nutrient transport across the placenta. It's complex.
And critically, the programming doesn't just stop abruptly at birth. Early postnatal nutrition is also a critical period. We see that rapid catch-up growth, which happens when infants born perhaps a bit small experience very rapid growth right after birth, and this is often more pronounced in formula-fed babies compared to breastfed ones. This rapid growth pattern is also linked to an increased risk of obesity and higher adiposity later in life. That suckling period, the first few months, is another really key developmental window for metabolic programming.
Okay, so if complex diseases like obesity and type 2 diabetes aren't just about a single bad gene, but this really intricate dance between multiple genes in the environment, starting even before birth, how exactly does that dance happen at a molecular level? This is where epigenetics comes in, right?
Yeah.
It offers a truly powerful explanation for these long-term effects.
Exactly. Epigenetics is key here. Imagine your DNA sequence, your genes, as the script for a play. Epigenetics doesn't change the actual words written in that script. It doesn't alter the underlying DNA sequence itself. Instead, it changes the stage directions, the lighting cues, the annotations on the script. It dictates how that play is performed, which genes are turned on, which are turned off, how strongly they're expressed in different tissues at different times. So it's all about changes in gene expression without altering the DNA code itself. And what's truly astounding, and maybe a bit unsettling, is that some of these epigenetic changes can potentially even be inherited across generations. There are two main mechanisms we talk about. First, DNA methylation. You can think of these methyl markers as little chemical sticky notes that get attached to specific spots on the DNA sequence. These notes can essentially tell a gene to be quiet or switched off, or sometimes loud and switched on. Second, there's histone modification. Histones are the protein spools around which DNA is wound to fit inside the cell nucleus. Modifications to these histone proteins can make the DNA either pack very tightly together, which generally silences the genes in that region, or become more loosely coiled, allowing the cellular machinery access to express those genes.
And crucially, these really intricate epigenetic processes aren't just random. They are profoundly influenced by environmental factors, especially diet. Nutrients like methionine, choline, folic acid, vitamin B12, they act as essential methyl donors in our biochemistry. They provide the raw materials for that DNA methylation process. So the mother's diet, and potentially the early postnatal diet, can directly impact the establishment and maintenance of these epigenetic patterns during critical developmental windows. And the real-world impact is becoming clearer. You mentioned the Dutch hunger winter survivor studies found they had less methylation, fewer of those sticky notes, on a key growth gene called IGF-2 compared to their unexposed siblings born before or after the famine.
Indeed. And other studies have found, for example, that obese men might show lower levels of methylation on genes involved in appetite regulation, like POMC and NPY. So these early life environmental conditions, particularly nutrition, but also stress, toxins can lead to potentially permanent epigenetic changes. They effectively create a lasting metabolic legacy, a biological memory of early life conditions that can predispose individuals to disease decades later. It's a profound reminder of the long.
So this deep dive into DOHaD and epigenetics, it really isn't just academic theory, is it? It provides a powerful and I think often overlooked framework for understanding the fundamental origins of many of the common adult diseases that you, as future medical professionals, are going to encounter every day in your careers. This understanding implies that for every adult patient you see struggling with, say, type 2 diabetes or hypertension, you almost have to consider their first 1,000 days, their early life history. It's not just about managing the symptoms presenting now. It's potentially about understanding, maybe even one day influencing, a biological program set decades earlier. It really reframes how you might take a patient history, doesn't it?
It absolutely does. And practically, this understanding underscores the immense critical importance of adequate and appropriate maternal nutrition in pair, not just during pregnancy, but ideally even before conception. That preconception and early prenatal window is incredibly sensitive for setting these trajectories. But what's truly critical here, and often the hardest part to address, is the socioeconomic aspect. Often, the women who are at the highest risk of poor nutrition or high stress during pregnancy are precisely those who may have the least access to high-quality antenatal care, support, and resources. This raises a really important, challenging question for all of us in healthcare about equitable access. How do we address the systemic barriers that perpetuate these cycles of risk?
Yeah, that's a huge challenge. But understanding these intricate mechanisms, from the fetal programming concepts to the epigenetic changes, it really does open doors, doesn't it? Potential doors for future interventions, especially if we can target that critical early life window. It feels like it offers hope for getting ahead of the curve, for maybe intervening early enough to disrupt the current devastating trajectory of the obesity and diabetes epidemic.
Exactly. Which leads to a final thought, perhaps a provocative one, for you to consider as you move forward in your careers. Given the profound, the lasting impact of these early life experiences on lifelong health trajectories, what fundamental shifts do you believe are most critical? What changes in public health policy, in clinical practice, maybe even in societal values, are needed to truly reshape the health trajectory of future generations? Think beyond just the individual clinical encounter. Consider the broader societal canvas, how we support families, mothers, children, right from the very earliest stages of life. What needs to change?